What am I going to teach about today? Sort of kind of running on empty. Wait a minute. I've got an idea. I'm going to teach about magnetism today. That's right. I'll go a long way for a gag. What I've got here is I've got a little light bulb sticking out of my head. And it's wired to me in a strange way, but I have it here to help me introduce the topic of magnetism, which is indeed the topic of this module. It's chapter 11 in your book. And first of all, you might be thinking, gosh, light bulbs, didn't we just finish with light bulbs in that last module about electricity? Well, it turns out, as you're going to find out in this module, electricity and magnetism are very closely related. I hope you were wondering where that energy came from, right? Didn't you see heat and light energy just a moment ago? There it is. Where does it come from? It turns out it comes from the kinetic energy of me turning this crank. And what we're going to learn about in this chapter when we study magnetism is that magnetism and electricity are very closely related. In fact, we actually use magnets to generate the electricity which lights that bulb. So pay very close attention when you're going through the reading in this chapter to focus on the relationship between moving electric charges and magnetic fields, as well as pay attention to the section about generators and motors.
I'm going to try to keep the chatter to a relative minimum this module because I've got a lot of video content, so I don't want to make this slideshow too long. But as this slide describes, with magnets, you must have a north pole and a south pole. There is the elusive monopole remains elusive. No matter whether you've got a horseshoe magnet or a single bar magnet, any kind of magnet has both a north pole and a south pole. As you're going to discover in this module, moving charges, electric charges, when they're moving, produce a magnetic field. And that's what's happening in the Earth. Of course, the Earth is a rapidly spinning planet. It spins once every 24 hours. And in its outer core, there is liquid or molten iron and molten nickel. These are both metals, and one of the calling cards of metals, as you learned in Module 7, is that metals have a lot of free electrons. So when you have molten metal, you've got a lot of free electrons, and of course, the inner core is spinning just like the rest of the Earth is spinning, and therefore these charges are in motion. And as you're going to find out, anytime you have charges in motion, you're going to have a magnetic field, and that is why the Earth does indeed have a magnetic field. The Earth has a magnetic north pole and a magnetic south pole. They are not in the same location as the geographic north pole and south pole, which is one thing that's very interesting about the Earth's magnetic field. The other thing that's interesting about the Earth's magnetic field is that it varies in its strength as well as in its polarity. So over time, the magnetic north pole and south pole are known to change places, to swap. And that is actually one of the pieces of evidence behind plate tectonics, believe it or not. So there's a lot of very interesting tie-ins to the Earth's magnetic field. Not only that there's tectonic activity on the Earth, but also, of course, without magnetic fields, the Earth would be bombarded with all kinds of charged particles from the sun and just from outer space in general. So without the Earth's magnetic field, life on Earth would not be possible. That's pretty heavy.
Okay, so I wanted to include a simulation that is not part of the main course. It's not part of your skill builders, your skills tests, your lab activities. The reason why it's not included is because this is a Java simulation, and unfortunately, Java does not play well on a lot of tablets and phones. So I don't have it as part of a regular activity, but I do encourage you, if you have a desktop or a laptop, go to phet.colorado.edu and check out this magnets and electromagnets simulation and play around with it for yourself. And I'm just going to sort of illustrate some of the functionality of this. Now, one thing that when you first load up the simulation, you're going to see a bar magnet with a south and a north pole. You're also going to see a little compass with a little needle. And again, the needle is the north end. and or the north-seeking end, and the white being the south pole of this compass. And so one thing you should notice is that when you start to move your little compass, you can actually move either one. You can move the bar magnet, you can move the compass, but what do you notice? That needle starts to move, and you are now physicists. You've been studying physics now for several modules, and you should notice that anytime something moves, such as this compass needle, you should immediately be thinking it doesn't move because it just decides I'm going to move. It moves because it's being forced to move. So one thing you notice immediately is that magnetism is a force. There's a magnetic force. And it's very much like gravity in the sense that we talked about this back in, I think, Module 2 when we first talked about forces. Some forces are contact forces, where you actually have to have two objects in contact with each other in order to have a force, to have an influence. But with gravity, gravity influences the moon, which is a quarter of a million miles away. It, it, it acts on planes and birds, things that are not in contact with the Earth. So gravity is a force that can act at a distance. And same thing with magnetism. If you ever try to put two magnets close together, you'll notice that they do influence each other without touching. And that's because the magnet has a magnetic field. That's what those arrows are that you see surrounding the bar magnet. And in fact, not only are they surrounding the bar magnet, but they're also internal. You can actually see a little magnetic field inside the magnet as well. But I encourage you to play around with this. May not necessarily need this field meter. That tells you the strength of the magnetic field at different points. And one thing you'll notice is that the strength of the magnetic field decreases the farther away you get from the magnet, and it gets stronger when you get closer. But I would generally just kind of keep that off. You may also want to switch over and show the planet Earth to help you understand. Whoops, I got to move my. I had my compass inside the Earth. One thing you'll notice is that the Earth indeed has a magnetic field. And the reason behind that is because the Earth is especially the outer core of the Earth, is a liquid metal. It's a molten metal. And of course, the Earth is spinning once every 24 hours, so you have a lot of metal that's spinning. And it turns out that metals have free electrons, and those electrons that are in motion set up a magnetic field, as you're going to learn later on in this module. So that's why the Earth indeed has a magnetic field, and thankfully we do, because that actually helps to shield us from a lot of damaging particles that would otherwise be hitting our planet. But anyway, I encourage you to play around with this little simulation, and what you'll notice is that indeed, not only does a bar magnet have a north end and or north pole and a south pole, but the Earth indeed has a magnetic North Pole and South Pole.
If you weren't able to go to the PHET simulation to play around with the bar magnet, you can go to a simulation that is bound to work on all your devices, whether you're looking at this on a phone or on a tablet that aren't Java or Flash friendly. You can still go to the Magnetic Field Skill Builder and play around with a bar magnet. Experience the field around a bar magnet using a little compass. As I mentioned when we saw the little slide about the Earth, charges, when they're in motion, do set up a magnetic field. Well, what is current? What is electric current? It's charges that are in motion. So sure enough, you would expect outside of a current carrying wire that there should be a magnetic field. In fact, you're going to experience this in one of your skills tests for this module.
Okay, so to prove the point that a current carrying wire does indeed have a magnetic field surrounding it, what I've done is I've taken a piece of wire and wrapped it around a compass. And in fact, my needle of my compass is essentially laying north to south along my wire right now. The wire is right now not carrying a current. It's got a bunch of electrons in it, but those electrons aren't going in any particular direction. They're just kind of milling around. There's plenty of free electrons. It's a metal that's in this wire that makes up the wire, but right now there is no current, and therefore there's no magnetic field. My compass is essentially aligned to the Earth's magnetic field. It's not being deflected right now. However, I've got my wire hooked up to my hand crank generator, and you're going to hear me crank it here in a second. And when I crank it, you should see a deflection of the compass's needle, which is going to indicate that there is a magnetic field that is interacting with the compass needle. Here we go. Okay, so remember the simulation that I was playing with just a few slides ago? This is the same simulation. The only difference is that I have now selected the electromagnet tab. So what we see here is that we have in this case, a coil of wire that's attached to a battery, and so we actually have set up a current. There's actually current flowing through the wire, and those little blue dots are supposed to be charges or electrons that are moving through the wire. So that is indeed current. We learned about that in the last module. Now remember what I said when we talked about the Earth. The Earth has a magnetic field because it essentially has electrons in its inner core, or outer core, that are in motion. They're moving. And it turns out that moving electrons, moving electric charges, will set up a magnetic field. And that's what we see here. We see these little compass pointers. These just indicate the strength of the magnetic field. I could click off the show field, I wouldn't see anything, but I can see the magnetic field that is surrounding this coil by virtue of clicking on that radio box. And notice that we know that you can actually show your field meter if you want. And again, the brighter those little indicators are, the stronger the field is. So it turns out, yes, the field is strongest essentially through the coil, and then it gets progressively less strong the farther away you get from the center. Another thing you can do with this simulation is you can actually vary the amount of voltage, and therefore, remember, voltage is the amount of electrical push. So notice as I decrease the push, notice I have less flow. Again, that should have been a lesson you learned last module. And as I decrease the flow, as long as I still have motion, I'm going to have an electric field, but the electric field has gotten weaker as I increase notice how they all get brighter. Those arrows get brighter. Of course, with no push, no current, no magnetic field. And you can actually flip it around and have the electrons travel the other direction. And what you see with my bar magnet, or my compass, is that the needle flips when you go from one polarity to the other, which is very interesting. And so what I've been using so far is just a battery, but we can also change the source and make it an alternating current, which by virtue of the name changes direction on its own. And therefore we see that the magnetic field is essentially always changing because of the direction of the current flow is constantly changing. So anyway, I encourage you to play around with the simulation and learn a little bit more about how you can turn a electric current, or how you get a magnetic field out of an electric current.
Now, of course, charges don't have to just be moving in a wire in order to have a magnetic field apply a force to them. They can actually be moving kind of individually. And that's actually how old cathode ray tube televisions used to work. And they're called CRT, cathode ray tube. Look them up. They're the big humpback televisions that your mom and dad used to have. Now, of course, everyone has flat screens. But essentially, old CRT televisions worked by having an electron beam that was deflected by a magnetic field that would move across the screen, and those electrons would crash into the screen and illuminate phosphors of red, green, or blue to create your color picture. It is really hard to overemphasize how important the discovery of electromagnetic induction was. This, of course, was in the 19th century. Michael Faraday and Joseph Henry discovered this, but it really revolutionized the industrial revolution and made electric motors possible. The fact that you could, and electricity generators, because you could now turn mechanical motion, moving a bar magnet in a loop of wire, you're able to convert that mechanical motion into electricity. That was really significant. It's not a chemical reaction. Volta had figured out how to make chemical batteries to create electricity, but here you were turning mechanical motion into electricity, which could then allow you to do any number of things. So it was a very, very significant discovery.
Okay, I wanted to show you another simulation that, again, is not part of the course because it is a Java simulation, but I hope it maybe will be useful to you if you want to play around with it. Notice this one is called Generator. You find it at phet.colorado.edu, and it actually has some of the tabs that we've already seen in action. We've seen the bar magnet, we've seen the electromagnet. This one also has one called pickup coil. This is the one that I want to feature for this part of the notes because what we have is a magnet, a bar magnet, and we have a coil of wire. And notice what happens when I move my bar magnet through my coil. We've got a little voltmeter there, and notice that we have a certain amount of voltage, a certain amount of electrical pressure that is generated. And the polarity of that voltage changes depending on how I'm moving my bar through the coil. You can also play around with a couple other features here. Well, first of all, you can put a light bulb there instead if you're more comfortable with that. And this just shows that indeed, when the magnetic field is changing through the coil, that will then cause a current to be induced. But notice that the blue dots, those are the electrons, only move when my current is changing. This is something you're going to wind up playing around with in one of the activities that will be required in this module. It's called Faraday's Law. And I'm actually going to show you the simulation that you'll be using for that one as well in the next slide. But you can play around with this one. You can change the number of loops you're dealing with and see how that impacts the current generated. In fact, it might be easier to use the meter for this. And notice that when I increase the number of coils, that also changes the voltage that I can generate here. So anyway, like I said, you can access this using the phet.colorado.edu generator simulator. Okay, so I wound up telling a bit of a fib 2 slides ago when I mentioned that I would talk about Faraday's Law on last slide, which was a little simulation where you can actually play around with it. You don't have to go to PHET to play around with it. It should be live in the PowerPoint. The problem being that live simulation prohibits me from recording audio on that slide. So I wasn't able to talk about Faraday's Law in that one, but hopefully you played around with the simulation and moved that bar magnet around. One thing that I hope you really pay attention to is the fact that if you put that bar magnet in the middle of the coil of wire, but we're not moving it, you should have noticed that there was no voltage produced. There was no current. When the magnet is just stationary, that means that the magnetic field is not changing. And so hopefully you realize that there's a connection between the amount of current generated in your loop and a changing magnetic field. That's the real key to understanding Faraday's Law. Now, one thing I hope you also picked up on was the fact that, well, once you had a changing magnetic field, it did set your charges into motion, right? But what do you know about moving charges? Don't moving charges themselves generate their own magnetic field? I hope you didn't miss that, because that's another very important thing to pick up on, and actually is going to be the key thing in another law called Lenz's law, which I'm going to illustrate next. So how long does it take an object to fall 75 centimeters? How far is 75 centimeters, you ask? It's about 2.5 feet. In fact, it's about as high as my desk here. So how long does it take an object to fall 2.5 feet? Let's find out. Ready, set, go. Now let's imagine this was a magnet. This is just a little piece of brass here, but what if it was a magnet? How long would it take it? Hopefully you remember from modules ago that an object that is in free fall, doesn't matter the mass, the material that it's made out of, it's going to fall with an acceleration of g, and that's what we call free fall. So it shouldn't really matter the material that it's made of. We're going to find out though that there's a special situation when the material, in this case a magnet, can have an impact on the fall time. For an object dropped from rest in free fall, we use the proper equation and determine that from 0.75 meters or 75 centimeters, the time of fall should be about 0.4 seconds. Now let's drop a magnet the same distance through a copper tube with
with a slit cut in the side so we can watch. The time of fall here is about 5 seconds, so clearly the magnet is not in free fall. There is another force at work. So here's an inside, if not overly well drawn view of what's happening to the magnet as it falls through the copper tube. And I've actually drawn the magnet in black, and I've shown it up at the top of the tube and then farther down in the tube. And as what you're going to notice is that as the magnet falls, it falls very slowly, and that's because the copper tube sees a changing magnetic field from the falling magnet. And this changing magnetic field actually induces a current in the tube. All those free electrons in the copper start to move. But of course, moving charges have a field of their own. And therefore, this current that's set up in the tube actually sets up a magnetic field that opposes the magnetic field that created it. And therefore, that's where our extra force comes in. So just like an object that is not in free fall has both its own weight, the force of gravity, and some other force acting on it, sometimes it's drag. In this case, it's the opposing magnetic force due to the induced current. This time we drop the magnet into a copper tube that has no slit cut in the side. Without the slit, we can actually get a stronger current and therefore a stronger force. The fall time of this one, about 8 seconds. So we've seen a pretty good illustration of Lenz's law, and we actually see another illustration of Lenz's law with this hand crank generator. Remember we talked about how it's work. You have to do work to crank this thing. Well, part of the reason is because, again, we've got a coil of wire here that's spinning inside of a fixed magnet. Okay, we've got essentially a changing magnetic field that's affecting this wire. The electrons start to move in the wire. That's how we generate a current. However, because we are now moving charges, those charges wind up creating a magnetic field of their own that opposes the magnetic field of the permanent magnet, and therefore the harder I crank, the harder I have to work. Lenz's law. Now, I hope you read carefully the sections in your book about motors and generators, because it turns out they're essentially two sides of the same coin. A generator turns mechanical energy into electrical energy. And that's what's going on in here. What I've actually got is this crank. I'm going to try to give you a close look at it. This crank is attached to a little axle. That axle then is connected to, there's some gears in here, and the gears turn a spindle that winds up turning a coil of wire inside of this housing. There's a coil of wire that turns, and there's a fixed magnet there as well. And so what you wind up having is a coil of wire in motion in a magnetic field. In the coil of wire, of course, there are a lot of free electrons because it's copper wire, plenty of electrons. Those electrons start to move. When we have moving electrons, we have current. That current then creates the light that we see. So as I crank this up, notice that I'm turning mechanical energy into electrical energy. That's what a generator does. It turns mechanical energy into electrical energy. A motor, on the other hand, takes electrical energy and turns it into mechanical energy. So motors are used in fans, and in fact, I can actually hook up two of these hand cranks and show you essentially that one's going to behave like a generator. It's going to create electricity, and the other one's going to behave like a motor. So all I'm doing is I'm going to connect these two guys together. And try to have the one, I'm going to hold one, and then I'm going to crank one of them. And, whoop. Isn't that neat? So the one is generating electricity. The electricity then is connected to that wire, and so then this one winds up behaving like a motor. It's taking that electrical energy and turning it into mechanical energy. Isn't that clever? Motors and generators.
I wanted to show you the hand crank generator again. We know what it does. I wanted to show you what happens when I disconnect one of the leads. So notice that I don't have a full circuit here, and notice my crank actually spins really easy when there's no load. But when I am connected, notice that my crank doesn't, it actually is much more difficult for me to crank this when there is a load compared to when there's not a load, which hopefully makes sense. You don't get anything for nothing in this world. We talked about simple machines, and that they can make they can reduce your force, but you wind up doing the same amount of work in the end, and that's really what's going on here. I'm getting heat and light energy, and it's not just coming from nothing. It's coming from the fact that I must do work. I must apply a force over a distance on this crank. So I'm expending energy in order to create energy. So now let's talk about how energy is created. The electricity you're using to charge your cell phone or whatever right now. Where does that come from? Ultimately, most of our forms of power production go back to burning something, whether it's coal or natural gas, or even in nuclear plants. Essentially what happens is you're creating heat, and either by burning or allowing radioactive materials to decay and getting the energy, but essentially you wind up creating steam. You take that heat and you boil water. When you boil water, you get steam. When you get steam, you compress that steam and force it to blow on essentially fan blades, turbine blades, which then spin the turbine and then essentially generate electricity, much like we've been doing. And this is true of wind power as well. Wind power, essentially you've got just wind hitting a fan blade, which then turns a coil inside of a magnet generating electricity. Even water, hydroelectric electricity production, comes from the fact that water is falling through a dam and falling on some fan blades. The water then turns the axle and gets the whole thing into motion. So ultimately, all power production essentially goes back into turning something. And the next question is, once you've generated electricity, how do you get it to your customers? And that's where Nikola Tesla and Westinghouse were very brilliant in the transmission of energy over long distances. Okay, so one more time with this phet simulation. Again, I'm using the generator simulation. And actually in the generator simulation, again, we've already played with the bar magnet, we've played with the electromagnet, we've played with the pickup coil. I encourage you, if you want to, you can play with the generator, but for this one, it's more than meets the eye. We're going to deal with transformers. And what you see with the transformers, we've got a battery hooked up to a coil of wire, and we've got another coil that is hooked up to a light bulb. Again, you can change it if you want to and make it a voltmeter if you wish. But one thing that's very important for you to understand is that, well, right now, what's happening? Nothing, really. Right? Do you see the light going on? No. What if we move this one coil a little bit? Notice we see a little bit of action in the light bulb, correct? Why is that? Because the field is changing. That's the important thing about a transformer, is that when you have two coils close to each other, if the one is producing a changing magnetic field, and the key there is changing, that will induce a current in the other loop. And you can actually make a changing field by switching your current source from being DC, direct current, which only goes in one direction, to AC. Notice that when you turn to AC, you'll see a much bigger, more convincing result in the light being generated by the light bulb, or if you wanted to switch it to your meter, you're going to see more wiggle in the meter's dial. But you can again change a number of loops in each of those and compare and contrast. The important thing is to understand that you need to have a changing magnetic field in order to induce a current in the secondary loop of your transformer.
It's a very interesting piece of scientific history when electricity was first used commercially, where electricity was produced in mass quantities and was then going to be transmitted to homes. a battle between Thomas Edison and Nikola Tesla. Very interesting if you want to take a look at this on Wikipedia or something of the sort. But essentially the story was that Thomas Edison thought that electricity should be produced as direct current and transmitted to people's homes at relatively low voltages. Tesla disagreed. Tesla thought that you could do it much more efficiently, with less loss, by first of all transmitting it as alternating current at much higher voltages. It turned out it was a much more efficient system. Edison tried to defeat Tesla's idea because he thought it was too dangerous by transmitting high voltages. And he actually electrocuted an elephant to prove his point. But it turned out that Edison was indeed wrong. It was much more efficient to transmit electricity over long distances with less loss by stepping it up to a high voltage and then stepping it back down when you got close to the point of delivery. In order to do that, you need transformers. And in order to have a transformer, you must be using alternating current.